My name's Tom Dick. I'm a math advisor for Texas Instruments, and this short video is part of the TI-Nfocus AP Calculus series. We're going to illustrate analyzing functions based on graphical information using the TI-84. What we have here is a graph that's already been prepared, and it's similar to the graphs that are presented on many free response questions over the last 20 years on the AP exam. You can see that this graph is piecewise, and it's made of line segments and pieces of circles. Now there's no formula given for this graph. It's just presented in graphical form, but we're going to be asked questions regarding both the derivative and the antiderivative of this graph. Now, for our purposes, we've actually kind of reverse engineered and figured out what the algebraic formula for this graph would be. And so you can see we've used the piecewise feature of the TI-84 to define a function where we have different formulas over different intervals. And so this is exactly the algebraic formula, piecewise defined, for the graph that you see here. Let's think about what the graph of the derivative of this function would need to look like. We can see over this first piece that we have a straight line, and so that's going to be a constant negative slope. We would expect our derivative to be a negative constant y value. On the next piece, it starts out very steep positive. When we get to the top of the quarter circle, 0, and the same for that next quarter circle piece. And then these two straight line segments will have a negative slope and then suddenly changing to a positive slope at that sharp corner. Now that we've taken a look at that, let's go to the y equals menu. And what we'll do is we've created y2, which is the derivative of our y1. And so let's turn that on, take a look at its graph, and see how our interpretation matches up. So this red graph is actually the numerical derivative of the graph in blue. And so sure enough, for that straight line segment, we're seeing a constant negative slope. Here where the slope starts out very positive and decreases to 0, we're seeing that for both of those quarter circle pieces, that behavior. And here's our sudden change from a negative slope constant to a positive slope constant reflected in the graph of the derivative. By the way, that glitch in the red graph is due to the fact we're plotting a numerical derivative. Okay, I'm going to go back to the y equals menu, and we're going to turn off y2, which was the derivative. And now we just have our original graph again, this piecewise linear and circle piece graph. And now we're going to think about, what if this was the derivative of a function? What would the antiderivative look like? So for example, here at x equal -1, where our derivative changes sign from positive to negative, we'd expect to see a local maximum on our antiderivative graph. At x equals 0, where this blue graph is changing from decreasing to increasing very suddenly, we would expect to see an inflection point in our antiderivative graph. Now as we follow the graph along these two quarter circle pieces, we can see that we've got a negative piece, and at this juncture at x equal 2, we've changed to positive. So we've changed derivative value from negative to positive. That'll be the location of a local minimum. And we can see a couple of other spots at x equal 5 and x equal 7. Our derivative graph changes from increasing to decreasing, or decreasing to increasing. These again will be inflection points on the graph of our antiderivative. Okay, let's take a look at the y equals menu. And we've set up an antiderivative graph. This is this definite integral function. It's an antiderivative guaranteed by the Fundamental Theorem of Calculus. We've used a lower limit of 0, and an upper limit is our variable x. And our integrand is our piecewise function whose graph is blue. We'll turn that on, And a definite integral graph is very computationally intensive and takes a long time to graph. So I'm jumping to a completed graph here. Both our original graph and the black graph is our antiderivative. And it's in a window that fits both graphs nicely. We can see that local maximum on the antiderivative graph at x equal -1, the inflection point at x equals 0, the local minimum at x equal 2, and we've got a couple of other inflection points. There's a subtle one at x equal 5 and a little bit more obvious one at x equals 7. To evaluate the antiderivative at x equal 5, that's actually a geometry question. We've got a sliver of area between the circle, the smaller circle, and the x-axis that'll be counted negative, and then we've got this actual area of the larger quarter circle will be counted positive. Let's actually go to the calculator and figure that out. So we had really a 2 by 2 square, 4, and 1/4 of a circle of radius 2. So pi times 2 squared over 4 is just pi. So 4 minus pi, but that was all under the x-axis, so we'll count that as negative. And then for positive, we'll need pi times 3 squared, or pi times 9, and it was a quarter circle. Divide by 4, add those two together, we come up with this numerical answer. Now let's check that by actually going back to our graph. I'm going to turn on the trace. It comes up on the blue graph, but we want to move to the black graph, which is our definite integral function. Notice it's taking a while to compute. Now we're at x equals 7, but let's jump to x equals 5 and wait for it to compute. And there's the value that's extremely close to what we calculated using geometry. Questions like these are really popular on the AP free response questions. They're so rich in the questions you can ask, because it requires you to think about derivatives and antiderivatives using graphical information, and I would expect us to see them for many years to come. You can see with this setup that by simply changing y1, we've got a brand new example to practice with. Well, that winds up this video. For more resources like these, please see education.ti.com.